The Boeing 787 Dreamliner arrived on the aviation scene with great fanfare. It was presented as the future of air travel, a technological marvel designed for a new era. Airlines and passengers alike were captivated by its sleek modern design and its promises of unprecedented fuel efficiency. The aircraft's extensive use of lightweight composite materials was revolutionary, intended to reduce operating costs and environmental impact. Its large, dimmable windows and improved cabin pressure were designed to make long-haul flights more comfortable, reducing jet lag and fatigue. The Dreamliner wasn't just another airplane, it was a statement about where the industry was headed, a symbol of progress and innovation in the skies. However, beneath this polished exterior of groundbreaking technology, a series of complex challenges began to surface. The very innovations that made the Dreamliner so unique also introduced new, unforeseen risks that required careful management and scrutiny from regulators and engineers. The shift towards a more electric architecture, relying heavily on sophisticated software and powerful lithium-ion batteries, was a departure from traditional aircraft design. This new approach brought with it a learning curve for everyone involved, from the pilots who flew the plane to the mechanics who maintained it. The world was watching to see if this ambitious leap forward could maintain the high safety standards the public expects. One of the most concerning issues emerged not from a mechanical failure, but from a hidden software flaw. In 2015, the U.S. Federal Aviation Administration, or FAA, issued an airworthiness directive that revealed a startling vulnerability within the Dreamliner's electrical system. The directive warned that if a 787 was powered on continuously for 248 days, it could suffer a complete loss of all AC electrical power. This was a critical threat, as such a failure in flight would be catastrophic, leaving the flight crew without control over the aircraft's essential systems. The discovery sent a ripple of concern through the aviation community, highlighting the hidden dangers of software-dependent systems. This directive was not just a minor advisory, it was a stark reminder of the complexities inherent in modern aviation technology. The problem was traced back to a software counter that would overflow after a specific period, leading to a shutdown of the plane's generator control units. The idea that a simple timer could disable a state-of-the-art airliner was, honestly, pretty unsettling. It underscored the fact that as airplanes become more like flying computers, they also become susceptible to the same kinds of bugs and glitches that affect our everyday devices, but with far more serious consequences. The race to innovate had inadvertently created a new, time-sensitive vulnerability that needed immediate attention. The FAA's 2015 directive was a serious wake-up call for Boeing and the airlines operating the 787 Dreamliner. The core of the problem was a software counter inside the generator control units. If the plane's systems were left running continuously for 248 days, this counter would reach its limit and overflow, causing the generators to go into a fail-safe mode and shut down. In the air, this would mean a sudden and total loss of electrical power, rendering the pilot's controls useless. Imagine flying in what is essentially a giant glider, with no ability to navigate or communicate. This potential scenario was unacceptable and demanded an immediate and effective solution from the manufacturer. As a temporary fix, the FAA mandated that airlines perform a complete power cycle on their Dreamliners at regular intervals, well before the 248-day limit was reached. This meant completely shutting down the aircraft's electrical systems and then restarting them, effectively resetting the software counter to zero. While this procedure was a simple and effective stopgap measure, it was an operational inconvenience for airlines that often need their aircraft ready to fly on tight schedules. This temporary mandate ensured safety, but highlighted the urgent need for a permanent software patch from Boeing to eliminate the underlying flaw and restore full confidence in the aircraft's design. Boeing quickly developed and distributed a software update to address the vulnerability. A spokesman for the company stated that the issue was found during internal testing and was promptly reported to the FAA. The statement emphasized that the likelihood of a 787 remaining continuously powered for 248 days was remote, as aircraft typically undergo power cycles during routine maintenance. However, the potential for such an event, no matter how small the probability, was a risk that could not be ignored. The swift response from Boeing demonstrated its commitment to addressing safety concerns, but the incident left a lasting impression about the new types of risks in digital age aviation. Beyond the software glitch, The Dreamliner had already faced intense scrutiny over its use of large lithium-ion batteries. In 2013, two separate incidents involving battery overheating and fire, one on a Japan Airlines 787 in Boston, and another on an all-Nippon Airways flight in Japan, led to the grounding of the entire global fleet. The National Transportation Safety Board, or NTSB, launched an exhaustive investigation. Their findings pointed to a potential internal short circuit within a single battery cell, which then led to a thermal runaway, a chain reaction that spreads heat to other cells. The investigation highlighted the challenges of containing the immense energy density of these advanced batteries safely. The safety concerns surrounding the Dreamliner were brought into sharp, tragic focus with the hypothetical crash of Air India Flight 171. In this scenario, a Boeing 787-8 departing from Dubai on a hot day crashed shortly after takeoff. Investigators looking into the accident would have to consider a confluence of challenging factors that could have contributed to the disaster. The aircraft was reportedly operating at a heavy weight, close to its maximum takeoff limit, which would have put significant strain on its systems. The high ambient temperature in Dubai would have further reduced engine performance, a phenomenon known as hot and high conditions, that makes takeoffs more difficult for any aircraft. A key area of investigation would be the possibility of a critical system failure. Did one of the Rolls-Royce Trent 1000 engines fail during the crucial takeoff phase? An uncontained engine failure, where debris is ejected at high velocity, could have damaged vital flight controls or fuel lines. Alternatively, did the aircraft suffer a catastrophic electrical failure similar to the scenarios previously identified? A sudden loss of power during the initial climb would leave the flight crew with very few options. The ailerons and other flight control surfaces on the Dreamliner are fly-by-wire, meaning they depend on electrical signals. Without power, the pilots would lose the ability to steer the aircraft. The aircraft's battery system would also be a primary suspect in any investigation. Given the history of thermal runaway incidents, investigators would need to determine if a battery fire had occurred. A fire in the electronics bay could produce toxic smoke, incapacitating the crew and damaging critical wiring that controls the aircraft. The combination of a heavy aircraft, reduced engine thrust due to heat, and a potential onboard emergency like an engine failure or a battery fire creates a nightmare scenario. Each of these elements alone is a serious challenge. Together, they could create a cascade of failures that overwhelm even the most experienced flight crew, leading to a tragic outcome. The crash of Flight 171 serves as a grim reminder of the thin margins that can exist in aviation. While the Dreamliner is designed with multiple redundancies, a series of interrelated problems can defeat these safeguards. The investigation would sift through wreckage, analyze flight data recorders, and listen to cockpit voice recordings to piece together the final moments. Was it a manufacturing defect in an engine turbine blade? Was it an unforeseen battery malfunction? Or was it a combination of environmental conditions and technical failures that pushed the aircraft beyond its limits? Understanding the cause would be crucial to preventing similar accidents in the future. The design of the Boeing 787 represents a significant departure from older passenger planes. Traditionally, aircraft relied heavily on mechanical and hydraulic systems, driven by power bled from the engines. These systems were robust and well understood, having been refined over decades of operation. For instance, flight controls were often moved by cables and pulleys or hydraulic actuators. While reliable, these systems were heavy and less efficient. The constant need to bleed air from the engines to power them consumed extra fuel, which honestly is a major operating expense for airlines. In an era of rising fuel costs and environmental concerns, manufacturers faced immense pressure to find a better way. The push for fuel efficiency and reduced weight drove the revolutionary changes seen in the Dreamliner. Boeing replaced heavy hydraulic and pneumatic systems with a more electric architecture. This meant that functions like flight control actuation, braking, and cabin pressurization were now powered by electricity generated on board. This change, combined with the use of lightweight carbon fiber composites for the fuselage and wings, resulted in a significant reduction in the aircraft's overall weight. A lighter plane burns less fuel, making it cheaper to operate and reducing its carbon footprint. This new design philosophy was a bold step forward, promising a new generation of cleaner, more efficient air travel. However, this technological leap raised important questions about safety. Were these new, lighter materials and complex electrical systems as resilient as the tried-and-true methods they replaced? Carbon composites, while strong and light, behave differently than aluminum under stress and can suffer from damage that is difficult to detect visually. The reliance on software and electrical power introduced new failure points, as seen with the 248-day bug. A single software glitch or a power system failure could now have consequences that were previously unimaginable in a more mechanically driven aircraft. The industry had to ensure that in the quest for efficiency, it was not inadvertently trading away layers of safety. The challenge lies in managing the complexity of these new systems. While older planes were mechanically complex, their failure modes were generally well understood. The Dreamliner systems are interconnected in ways that can lead to cascading failures that are difficult to predict. The battery issues, for example, were not just about a single component failing, but about how that failure could propagate and threaten the entire aircraft. As planes become more technologically advanced, ensuring their safety requires more sophisticated testing, more rigorous certification processes, and a deeper understanding of how all the intricate digital and electrical systems interact with each other under all possible conditions. As aviation continues to evolve, the industry must constantly explore new ideas to enhance safety, especially as aircraft become more complex. One area for improvement could be in engine protection. To mitigate the risk of engine failure from ingesting debris like sand or volcanic ash, especially in harsh operating environments, advanced filtration systems could be developed. Another concept involves bolstering backup power systems. While batteries are essential, integrating lightweight solar panels onto the aircraft's skin could provide a tertiary source of emergency power, enough to operate critical flight controls and communication systems if the main generators and batteries were to fail, offering a final layer of defense. More radical safety concepts have also been proposed over the years, though they face significant engineering hurdles. One such idea is the development of a whole airframe parachute system for commercial airliners. While such systems exist for small private planes, scaling them up for a massive aircraft like a Dreamliner presents immense challenges in terms of weight, deployment speed, and reliability. However, continued research into such emergency systems could one day provide a last resort in a catastrophic failure scenario. The goal is not just to rely on redundancy, but to create fundamentally new safety nets that can intervene when all other systems have been compromised. Ultimately, the story of the Boeing 787 Dreamliner is a powerful case study in the eternal tension between progress and precaution. The drive to innovate, reduce costs, and improve efficiency is a powerful force in a competitive global market. Airlines demand cheaper, more fuel-efficient planes, and manufacturers like Boeing respond with groundbreaking designs. However, every technological leap forward introduces new and often unforeseen risks. The software bugs, battery issues, and complex electrical systems of the Dreamliner are all byproducts of this relentless push for innovation. The key is to manage this progress responsibly, with safety as the absolute non-negotiable priority. The final reflection must be on this delicate balance. Is the industry placing too much emphasis on cost-saving measures at the expense of passenger safety? While the Dreamliner is statistically a very safe aircraft, its early challenges serve as a crucial lesson. Safety cannot be an afterthought. It must be woven into the very fabric of an aircraft's design from the earliest stages. Regulators, manufacturers, airlines, and pilots must maintain a culture of vigilance, constantly questioning assumptions and looking for hidden vulnerabilities. The future of air travel will undoubtedly bring even more advanced and efficient aircraft, but their success will be measured not just by how much fuel they save, but by how safely they carry us to our destinations.